Let's begin with an introduction to bitwise operations. These operations involve manipulating data at the most fundamental level, the bit level. These are the smallest units of information that a computer can process. We will explore what bitwise operations are and why they hold significant importance in computer science. Here are the core bitwise operators. First is the AND operator, represented by an ampersand. It performs a bit-by-bit comparison and returns 1 only if both bits are 1. Next is the OR operator, denoted by a vertical bar. It returns 1 if at least one of the bits is 1. Then comes the XOR operator, represented by a caret. It returns 1 if the bits are different. The NOT operator, denoted by a tilde, inverts the bits. A 0 becomes a 1 and a 1 becomes a 0. The left shift operator, written as 2 less than signs, shifts bits to the left. Finally, the right shift operator, written as 2 greater than signs, shifts bits to the right. Let's consider an example of an AND operation. In this Python code, we perform an AND operation on the numbers 5 and 3. The binary representation of 5 is 0101, and 3 is 0011. The AND operation results in 1, which is 0001 in binary. The code then prints the result. Now let's explore the key properties of the XOR operation. First, it is self-inverse, meaning a XOR equals 0. It has an identity element, so a XOR 0 equals A. It is commutative, meaning a XOR B equals B XOR A. It is also associative, meaning a XOR B, XOR C equals a XOR B XOR C. Let's look at a table for XOR operation. Now let's explore some of the applications of the XOR operation. It's used for efficient variable swapping without needing a temporary variable. It's useful for finding a single non-duplicated element in a dataset. It is used in simple cryptographic operations. It allows for memory-efficient toggling of flags. Finally, it is used for error detection in communication protocols. The formula for swapping two numbers using XOR is A equals A XOR B XOR B. Here we will explore how to swap variables using the XOR operation. First, XOR A with B and store the result in A, using the formula equals A XOR B. Next, XOR B with the new value of A and store the result in B. Using the formula B equals B XOR A, which simplifies to B equals B XOR XOR B, resulting in B equals A. Finally, XOR A with the new value of B and store the result in A. Using the formula equals A XOR B, which simplifies to A equals A XOR B, XOR A resulting in A equals B. Let's walk through an example. If we start with A equals 5 and B equals 9, after the first XOR operation, A becomes 12 and B remains 9. Next, A remains 12 and B becomes 5. Finally, A becomes 9, and B remains 5, successfully swapping the values without a temporary variable. The Python code shows how to implement the XOR swap. First, it prints the initial values of A and B. Then, it performs the XOR swap algorithm. Finally, it prints the final values of A and B. Let's see how to find the single non-duplicated element using XOR. Here is the problem definition. Given an array where every element appears exactly twice, except for one element that appears only once, find that single element. For example, in the array 4, 1, 2, 1, 2, 7, 4, the number 7 appears only once. The key insight is that when we XOR a number with itself, we get 0. An XOR with 0 returns the original number. Therefore, XORing all elements will cancel out the pairs, leaving only the single element. This Python code shows how to find the single element using XOR. First, it initializes the result to 0. Then it XORs all elements in the array. Finally, it returns the result. Let's explore the fundamentals of bit masking. A bit mask is a binary pattern used to extract or modify specific bits within a binary number. Consider this example where we have a value 10101101 and a mask 00110000. Applying AND operation between the value and the mask isolates bits at positions 2 and 3, counting from the right and starting from 0. The result gives us only those specific bits, 00100000. Here are common bit mask operations. Extracting specific bits from a value. Setting specific bits to 1. Clearing specific bits to 0. Toggling specific bits. Checking if specific bits are set. The Python code shows how to create a bit mask. To create a mask for the third bit, we left shift 1 by 2, resulting in 00000100. To create a mask for bits 1 through 3, we left shift 1 by 3 and subtract 1, resulting in 00000111. Let's explore the core operations of bit masking. Setting a bit is achieved by performing an OR operation with a mask that has 1 only at the target position, using the formula number or equals 1 left shifted by position. Clearing a bit is achieved by performing an AND operation with a mask that has 0 only at the target position, using the formula number and equals the inverse of 1 left shifted by position. Toggling a bit is achieved by performing an XOR operation with a mask that has 1 only at the target position, using the formula number XOR equals 1 left shifted by position. Checking a bit is achieved by performing an AND operation with a mask and checking if the result is non-zero, using the formula number and 1 left shifted by position, not equals 0. The Python code shows how to perform these bit operations. It starts with an original number. Then it sets the bit at the given position. Next, it clears the bit at the given position. Finally, it toggles the bit at the given position. Let's explore how to check specific bits and determine if a number is a power of 2 using bit masking. To check if the nth bit is set, use the formula if number and 1 left shifted by n, not equals 0. This returns true if the bit at position n is 1. To check if all bits in a mask are set, use the formula if number and mask equals mask. This returns true if all bits set in the mask are also set in number. The Python code shows how to check if a bit is set at a given position. To check if a number is a power of 2, use the formula if n and n-1 equals 0 and n is greater than 0. This works because a power of 2 has exactly 1 bit set to 1. Subtracting 1 from a power of 2 flips all bits up to that position. As a result, performing an operation between n and n-1 will result in 0 if n is a power of 2. The Python code shows how to check if a number is a power of 2. Let's explore a bit manipulation problem. Counting set bits. Given an integer, count the number of bits set to 1 in its binary representation. For example, the number 42 has a binary representation of 101010, with 3 set bits. The number 127 has a binary representation of 111111, with 7 set bits. There are 2 techniques to solve this problem. Brian Kernighan's algorithm, which uses the property n and n-1, clears the rightmost set bit of n. The lookup table technique, where you can use pre-computed values for bit counts in smaller chunks. The Python code shows how to implement Brian Kernighan's algorithm. It clears the rightmost set bit and increments the count until n becomes 0. Let's explore how to generate subsets using bit manipulation. Given a set, find all its possible subsets. Bit manipulation can be used to efficiently generate all possible subsets of a set. Consider this bit mapping for the set consisting of A, B, and C. The empty set is represented by 0, 0, 0. The subset containing A is represented by 0, 0, 1. The subset containing B is represented by 0, 1, 0. The subset containing C is represented by 1, 0, 0. The subset containing A and B is represented by 0, 1, 1. The subset containing A and C is represented by 1, 0, 1. The subset containing B and C is represented by 1, 1, 0. The subset containing A, B, and C is represented by 1, 1, 1. The Python code shows how to generate subsets using bit manipulation. The total number of subsets is 2 to the power of n. For each number from 0 to subset count, create a subset based on the bit pattern. Check if the jth bit is set, and if so, append the corresponding element to the subset. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.